Hello, everyone. My name is Alex Carr, and thank you for coming to my talk. I'm going to be discussing some work that I've done on modeling sonic boom propagation in the atmospheric boundary layer and near the lateral extent of the boom carpet. I'd like to start off by acknowledging the NASA Fellowships Management Team, as well as the NASA Commercial Supersonic Technology Project and the NASA Langley Structural Acoustics Branch for supporting this work. I'm very grateful for your support. So just to quickly go over a motivation and background of what I'm doing. So many sonic boom prediction codes today are based on a traditional ray theory approach, and they can't make predictions in the shadow zone. If we compare predictions at the lateral extent of the carpet and into the shadow zone that are made by a traditional ray theory code, one such popular one is PC boom. If we compare these predictions to actual microphone measurements near the lateral extent of the carpet and beyond, we can see that PC boom underpredicts the sound exposure level within the carpet near the lateral extent of the carpet, and then there's a slight overprediction where the end of the sonic boom carpet is predicted to be at. Whereas the microphone measurements show just this steady decrease in sound exposure level beyond the lateral extent of the carpet. And so the significant sound exposure level up to almost one nautical mile beyond the predicted carpet isn't accounted for from traditional ray theory codes. So some of the consequences of this are that our computational prediction data sets are incomplete, and then decisions about community response testing areas and flight paths of future supersonic commercial aircraft may be based on narrow carpet predictions. So the objectives of this research are to develop an efficient code that's suitable for parallel computing that will be able to predict the effects of turbulent scattering and ground diffraction on the sonic boom waveform, thereby also being able to predict sound propagation into the shadow zone region. And this is what most of the talk is going to be focused on. And then some future objectives of the research will be to relate some of the parameters of turbulence to waveform characteristics and look at that and see how those two phenomena are related. And then also looking at starting to predict some of the fall-offs in the sound exposure levels beyond just the traditional sonic boom carpet. So the code is based on the FLHOWARD equation, which is based on an equation derived by Kuhler. So Kuhler performs a decomposition on the Navier-Stokes equations into acoustic fluctuating components and the flow components, where the flow components are assumed frozen in time. So that's just saying that the time scale at which they move at is much smaller than, or is much larger than the time scale of the propagation of the waveform. Skipping several steps, we can obtain a governing equation for the acoustic pressure, P tilde here. That has terms on the right-hand side that account for turbulence interactions, as well as nonlinearities and thermal viscous absorption. And this equation is accurate up to third order in the acoustic Mach number. So in order to obtain a numerical solution to equation 3, I followed the steps of Liu K, who applies a wide-angle parabolic approximation to heterogeneous terms, and then obtains a partially one-way equation for phi, which is the acoustic potential. D, H, N, and A represent diffraction, heterogeneous terms, nonlinearities, and absorption, respectively. And you might be able to notice that when neglecting diffraction and the heterogeneities, we can actually see that equation 4 will reduce to the Berger's equation, which is the governing equation of PC boom. So in order to test the accuracy of the code, I looked at 4 different benchmark cases to test each physical effect. Looking first at diffraction, I chose to examine the case of diffraction by a circular aperture. So figure 4a just represents the maximum pressure at each propagation distance downstream. The simulation results are in blue and the exact solution is in orange. And you can see in the near field, the simulation and the exact solution match quite well. And then as we get to the far field, the simulation captures the trend. However, we see some oscillations here from reflections from our outgoing boundary conditions. So that's something we need to address further. For heterogeneities, or the flow and the turbulence effects, we can look at scattering by a spherical temperature heterogeneity in the middle of the domain. So in the middle of the domain, we essentially have a sphere that has a 5% increase in the sound speed. And when we propagate a plane wave toward the sphere, you can see that our simulation results don't capture any of the backscattering within the sphere and forward of the sphere. And that was expected since our simulation is a one-way propagation. So we didn't expect to capture that. However, we are fairly happy about our ability to capture the forward propagating pressure solution and capture the subsequent pressure rise. So that gives us good confidence in the ability to capture the forward solution. For nonlinear effects, we can propagate a sine wave nonlinearly in the domain and compare with the Blackstock bridging function, which is just pretty much a function that bridges two solutions, one before the shock formation and one beyond shock formation. And you can see for sigma 1, 3, and 5, where sigma is the shock formation distance, our algorithm in blue agrees quite well with the Blackstock bridging function. And then looking further at the absorption in the domain, we can account for molecular relaxation and thermal viscous effects through the work of Bass et al., reference 7 here. So they give a functional form for alpha in the atmosphere that accounts for molecular relaxation of nitrogen and oxygen, as well as the thermal viscous effects. And then we can just say that the absorption acts to attenuate some of the higher frequency sounds. So it's just the solution is multiplied by an exponentially attenuating factor. And then we can compare that to the problem of Mendus. And when we do that at a shock formation distance of 3, we can see that our simulation pretty much overlaps with the solution of Mendus. And so that gives us confidence in our ability to predict these absorption effects. So it's important that we can model the atmospheric mean and turbulence quantities in our code, because measurements of these quantities in the atmosphere aren't really readily available. And if we want to account for flow and turbulence effects on the sonic boom waveform, we need to model these in our computational domain. So turning our attention first to the mean velocity and mean temperature profiles, I chose a Monin-Obuhkov similarity theory to model these two quantities, and then also chose the functional forms of psi m and psi h from Wilson 2001, who chose these functions to have correct asymptotic behavior as the non-dimensional height goes to negative infinity. So the case of free convection, essentially. So it's important to compare the profiles of U and T that we have in our code with measurement. So I chose to compare these with SODAR data that was measured at NASA Armstrong Flight Research Center. And you can see the plot on the right-hand side has non-dimensional U on the bottom axis, and then the non-dimensionalized altitude on the left axis, or the vertical axis. And we can see that the SODAR data, the red dots here, agrees quite well with the most profiles. So that gives us good confidence that our code is able to model these mean quantities in the atmosphere. Beyond just modeling the mean quantities in the atmosphere, it's important to construct a turbulent field in the computational domain so that we can account for the interaction of turbulence with the sonic boom waveform. To do so, I chose to use the spectral domain algorithm outlined by FLHOWARD et al. Essentially, this algorithm computes the turbulent velocities by taking an inverse Fourier transform of this function w. And w is a function that's determined from a composite spectral model. So I chose the von Karman spectral model, and in the next slide I'll get into why that decision was made. And so once W is determined from this multiplication of the H matrix with the complex Gaussian random number vector, I can then take a inverse Fourier transform and obtain a random turbulent field. So I chose to check the turbulent kinetic energy spectrum by comparing with measurements from wind tunnel grid turbulence. I chose to compare with measurements of wind tunnel grid turbulence because that most closely represents isotropic turbulence in a real case, in a real life scenario. So figure 7a shows the comparison of the model spectrum computed and compared against the measurements at 3 different downstream locations from the grid for the wind tunnel grid turbulence case. This data is from Compla and Gorson. And as you can see, there's a pretty good agreement for each model spectrum with the data. So that gave us good confidence that the von Karman spectral model would be a good approximation of the turbulent kinetic energy across all frequencies. So once we have the model spectrum, then I used that to generate the W function and then to compute the inverse Fourier transform to get our turbulent velocity field. Once I had the turbulent velocity field, I computed the autocorrelation, which is just computed using Taylor's hypothesis, assuming that delta x, so x is going to be the direction in which the main direction of the flow, essentially. And then assuming that delta x is equal to the convective velocity multiplied by the delta t, we can compute an autocorrelation averaged over about 500 different data sets. And as you can see, the autocorrelation trends match quite well with the experimental data. However, we do tend to see a general overprediction of the autocorrelation compared with data until about until we start getting more downstream. Overall, though, compared to possible other methods of generating a turbulent field that might not obtain any correlations, we believe that this is a good beginning and a good start. So just to recap and talking about future work. So a prediction tool was developed that accounts for diffraction, scattering, absorption, and nonlinear propagation. A turbulent field was generated in the computational domain based on a similarity theory and also a spectral domain algorithm. And then the comparison of the mean flow field as well as the turbulence flow field matched some of the data that we've looked at for isotropic grid turbulence and also measurements in the atmosphere using a SODAR. So those are some promising results for the current model that we have in our code. For future work, it's important to obtain comparisons with current codes like PCBoom and see where some of the differences in the waveforms might be and what those differences are. It's also important to start looking at these diffraction effects from the ground, so implementing some ground boundary conditions and starting to obtain predictions near the lateral extent of the sonic boom carpet. And then we're also going to look at obtaining some predictions with atmospheric turbulence and looking at waveform characteristics and how to relate them to different turbulence characteristics of the atmospheric boundary layer turbulence. So thank you everyone for watching my presentation, and I guess I'll take any questions now.